By the end of this video, you should be able to understand what exactly linear and angular velocity are, how they relate to each other, and what the radius does to either the linear velocity or the angular velocity. And this is when we're talking about circular motion problems. First, let's talk about what exactly is linear velocity. Well, velocity or speed is how fast something's going. But how do we measure this? Well, we would take the distance and divide it by the time. And this should give us velocity or speed. For example, let's say that a car went 276 miles and it did that in 4 hours. Then what would we say? Well, we would say that the car was going 69, basically 276 divided by 4, 69 miles per hour. So when we talk about linear velocity, basically linear velocity is distance over time. And if we think about what the units might be, we already know that this could be miles over hours, or it could also be kilometers per hour, or even centimeters per second, or even feet per minute. Basically, the unit on top has to be some kind of distance that we're measuring, and the unit on the bottom has to be some kind of time that we're measuring. So it's distance divided by time to give us the linear velocity. When we think about driving a car, we normally think about driving in a straight line. And we would take the distance here and figure out what time it took us to drive that distance. And we would divide it by the time, and that would tell us how fast we're going. In the example that we just looked at, for example, if from point A to point B, if we traveled along that straight path from point A to point B or city A to city B, and it was 276 miles, and it took us 4 hours to do it, well, we know that 69 miles per hour is how fast we went. But what about if we were talking about traveling in a circular path? How do we measure distance on a circular path? You might recall that we had talked about how we would describe, let's say, the partial distance from here to here. What do we call that? We can't call it circumference because we've only gone a certain amount around the circle. It might be a fraction of the circumference, but we use the term arc length to describe that path or that distance that we've traveled around the circle. So from here, this is point A and this is point B, then the distance that we traveled on that circular path is called the arc length. So how would we measure linear velocity on a circle then? Well, just as before, we would take the distance, this time we're calling the distance the arc length, and we would divide that arc length by the time that it took us to do that, and this would give us the velocity. In other words, our linear velocity. So we could describe this actually using a formula as well. So remember we said this distance here corresponded to our arc length. We remember that we had this formula for arc length where S was equal to r times theta, where r was the radius that formed a certain angle theta. So this would be r and that would be r. So if we replace that in our formula, then our formula would say r times theta, because that's the same as the arc length, divided by the time. We'll just replace that with t. So if we wanted a formula for our linear velocity, we could say that linear velocity can be represented by the radius times theta over time. What does angular velocity? Well, angular velocity is just as it sounds. Velocity, if you remember, we said was distance divided by time. Or in other words, we're measuring how something changes over time. But if it's angular velocity, instead of talking about the distance, we're talking about how the angle is going to change over time. We can represent this by saying, let's say theta represents an angle that we've moved through, and t represents the time that it took us to do it. Then our angular velocity, which we normally use this omega to represent angular velocity, omega is going to be basically the same as theta divided by t. And how exactly do we measure angular velocity? Well, think about how we can measure angles. This theta could be measured in maybe radians. And this t is going to be some measurement of time. So it could be something like seconds. So if we see radians per second, or radians per minute, or radians per hour, then that's a good indication that what we have is the angular velocity. Remember also that radians can also be represented in terms of revolution. Remember that one revolution around the whole circle represents 2 pi radians. So we can actually do some conversion and change radians to a certain amount of revolutions. So if we have revolutions per second, or revolutions per minute, or revolution per hour, then we're also measuring angular velocity. So what have we said so far? We have two quantities. One is angular velocity, and the other is linear velocity. So let's compare them. For angular velocity, we use the symbol omega is equal to theta, the angle that we've gone through, divided by the time that it took us to change. We said that for our linear velocity, it's basically the same as our radius times theta divided by the time that it took us to change. So what do we notice about the two formulas? Let's say we focus on the fact that omega was the same as theta over t. Well, we have theta over t in this formula. So what that means is that we can rewrite the linear velocity as r, or the radius, times omega. What are some other observations that we notice? This formula on this side, does it have anything to do with the radius? No. So the angular velocity is independent of, if I can spell independent, let's try that again. It's independent of the radius. So it doesn't matter what the radius is, the angular velocity will be the same. So let's say we took, for example, a wheel, and suppose that we taped the letter A here, and then we decided to tape the letter A out here. And if we measured the angular velocity of the blue A, or we measured the angular velocity of the green A, basically they would be the same. because even though the radius for this A is smaller than the radius for this one, if we look at the formula, basically it doesn't matter what the radius is, theta over t will be the same for either one. In other words, the angle that I have for this A and the angle that I have for this A would be the same angle if I moved it, let's say, over here. So that A and that A. Or let's say that I moved it over on this side. Both A's are moving exactly at the same time. And so what that tells us is that angular velocity is independent of the radius. So when you see a problem, it's asking for the angular velocity, you don't even need the radius. But if you look at the linear velocity, that's a different story. Notice that linear velocity has the radius as a part of its formula. That means the bigger this number gets, the bigger this number is going to get. In other words, as the radius increases, the linear velocity also increases. So basically, we can say that the larger the radius is, then the larger that we're going to have the velocity be. So in other words, if we take that same example where we've pinned the letter A here and we've pinned the letter A here, and we decide to spin our wheel, then what should happen is the A out here has a larger radius than the A in here. So in other words, this A, the blue A, will appear to be slower than this one is. In other words, the green A, because it has a larger radius, is going to have a larger linear velocity. And the blue A, because it has a smaller radius, is going to have a smaller linear velocity. So we're going to demonstrate this in class. And so you'll see this and you'll be able to really comment, and hopefully that helps you to see exactly the difference between linear and angular velocity. One quick note, remember the units: angular velocity, radians per unit of time, or revolutions per unit of time. Linear velocity, that's going to be whatever the distance is. Could be centimeters, could be kilometers, could be meters, could be miles, whatever it is, over time, over some unit of time. So it could be seconds, could be minutes, could be hours, we don't know. But all of these units would tell us that we are dealing with linear velocity.